Okay, so welcome back to another video. So here today we have an indefinite integral of the square root of x times the arctangent of x divided by 1 plus x squared dx. So similarly, I did a video in the past. It was, I think, titled the Trigonometric Golden Integral, where the golden ratio was involved for 1, and it was placed under the square root sign for 1 over here, and then another one where it was actually as the exponent x to the power 5, but treated that as a quantity and then square. So you might be thinking, is it like the work, is the method of evaluating that integral similar to this one? And no, it's not. So for one, there really isn't a inverse tangent identity we'll be using to evaluate this integral, unlike the other. But also, secondly, if after going through some work and just giving you some formulas that we're going to use to evaluate this integral, there's actually the beta function and the gamma function involved, which was not used in the other video. So if you haven't checked that video out, I'll leave that link in the description below. But you'll expect a lot of substitutions, U-substitutions, and there's a lot of algebra manipulation, especially we'll be dealing with partial fraction decomposition. So, but from that, I'm not really going to go too much into the process because those calculations are pretty straightforward. So it's more along the lines of it's just long and tedious. But validating is up to you whether you want to. If I don't convince you otherwise. So other than that, let's actually just jump in. We start with so I'll just call this capital I, but let me get to that in a sec. But first, we'll actually do a U-substitution. So I'll let U equals the square root of x. Then if I just solve for x on its own, then we have that U squared is equal to x. Then differentiate both sides. So dx is equal to 2u du. Then if we just plug everything back in, so this entire integral that we're given is called capital I. So of course, if we plug in all this back in, so for 1, I can factor out 2 outside of our integral. And we don't really need to change the bounds because it's just going to stay the same. If I just plug 0 for x, that's still going to be 0. And if I plug infinity, it's still going to be infinity. So square root of x is going to be u. But also with this new dx differential, so u du, after just factoring the 2 outside, so we have a u square, then multiplied by arctan of u square. Then all this being divided by 1 plus x squared, just substitute the x in. So this will be u to the power 4th du. We can actually suppose that if we were to define a little generalization integral, and that says that for some function, we call this f of a, and then we set this equal to the integral above, like I said, with a different added parameterization. So that will be saying that u squared times arctan of a times u square, all this divided by 1 plus u to the 4th, and then du. Clearly, we can see that I is going to equal 2 times, and if we plug 1 for a, then it's exactly giving with this improper integral. So basically, in the gist of it, we just need to calculate what 2 times f of 1 is going to equal to, finitely exactly. Starting off with using Feynman's trick, we can actually differentiate this integral in respect to a. So by applying that, so that's not that difficult to see, that f prime of a is going to give us, the following. So of course we still have this improper integral. Then so u square, or rather we're differentiating in respect to a. So so this is 1 over. So I'll write this in full, actually, I'll just save the explanation. So u to the power 4, then divided by 1 plus u to the power 4, multiplied by 1 plus a squared u to the power 4th, and then du, simply because, the derivative of arctangent is 1 over 1 plus some parameter square. You just put this back in, and that's where it comes down to. All right, and yeah, I put the du. All right, so now we have to figure out how to integrate this, but by doing so, if you learn in calculus, we're actually going to be using some partial fraction decomposition. So by PFD, and I'm just going to save all this work, you'll see that specifically this function, I'm just going to write out what our integrand first, and then write out the results of that decomposition looks like. Our following decomposition is going to look like this. So we're going to have a 1 divided by a squared minus 1 multiplied by 1 divided by 1 plus u to the power 4th, subtract 1 divided by a squared minus 1, then multiplied with 1 divided by 1 plus a squared u to the power 4. What I can do here is I'm actually going to rewrite this a little bit differently. So what I'll do is that I'm just going to factor out a negative from here and here. And so what that means is that I can actually just interchange these denominators. So the 1 will come first and then the a squared will come next to subtract a squared. So from here, then that means that the following, and I'll also just skip a couple steps as well. So now plugging this back into, the integral back, of course. So after all this, we're gonna get that this is 1 divided by 1 subtract a squared multiplied by an improper integral of 1 divided by 1 plus a squared u to the power 4 du. Then subtract, so 1 divided by 1 minus a squared multiply integral 0 to infinity of 1 divided by 1 plus u to the 4th, then du. We're going to start now from this whole thing that we need to calculate these integrals. So we're actually going to evaluate one integral at a time. So we're going to first evaluate this integral over here. So let's start off with that. For the integral from 0 to infinity, 1 divided by 1 plus a squared u to the power 4th du. So let's do a u sub. So suppose I'll let u equals the square root of tangent t then divided by a. Then that means if I just perform this differentiation for both sides, so we're going to get that du is going to equal 1 divided by the square root of a, and then we just multiply this by secant square of t divided by 2 times the square root of tangent t dt. And so from there, we just have to plug them back to this integral. So I'm gonna denote this equal sign to say that we're coming from over here just to save some space. So then, and then when we calculate our new bounds, simply if we plug 0 for u, then we can see that tangent of t is going to be 0. And if we plug infinity, then we can see that t is going to equal 0. And then for the other one for infinity, then t is going to equal pi over 2. So we have our new bounds situated. And then if I just plug all this back in, so let's see, I have 1 divided by 1 plus a squared, then plug this back in. So it's a square root and then to the 4th, so that means we're actually left with quantity square. So tangent t divided by a, quantity square. Then we just multiply with the secant square t divided by 2 times tangent of t and dt. Simplify everything here. So let's see, tangent t and then a squared. So a squares will cancel. 1 plus tangent square t. We know that's the trig identity that's also equal to secant square t. Those two will cancel each other out. I'll factor out the 1/2, and also I forgot to put in the square root of a on the bottom. So let me add that in. So I'll factor out the 2 and the square root of a outside of our integral. So we have 1 divided by 2 times square root of a divided by, or multiplied by the integral of 1 divided by the square root of tangent t dt. You'll notice that we can actually rewrite the square root of tangent t in terms of trigonometric functions of sine and cosine. So by doing so, we would have a new rewritten integral and say that this is 2 times the square root of a. Then multiply, that's also supposed to be a pi over 2 over here. So we have a pi over 2 over here, and we write all this out. So in terms of with the exponents of those trig functions, so now we would have a cosine of 1/2 t, and then multiply by sine of negative 1/2 t dt. So this actually should look familiar to you because this is actually in form of a beta function and represent in the integral representation with trig functions. So what that says that for specifically for capital B of our 2 inputs, let me actually put it over here so it's okay. Capital B of uv is going to equal 2 times the integral from 0 to pi over 2 of sine of our input 2 u minus 1, then I'll call this t, and then cosine of 2u minus 1, or actually that input's supposed to be v, so 2v minus 1, and then t, then dt. And so from here, if we just replace everything for this new integral over here, so now we write that same integral again, the integral from 0 to infinity of 1 divided by 1 plus a squared u to the power 4th du. We would have, let's see, so back here, so we have 1 divided by 2 square root of a, then use the new expression of the, plug in your parameters for beta, and you see that beta is going to equal capital B, and then the inputs for U and V are going to be 3/4 and then 1/4. We need to use another formula for in terms of gamma functions, and that says that, Euler's reflection formula, or for gamma of U multiplied by gamma of 1 subtract U is equal to pi divided by sine of pi times U, because that will actually help us evaluate the beta function. So let's actually work on that. Pretty straightforward to see that we just plug in everything we see, so 3/4 and then 1/4. So then this will be gamma of 3/4 multiplied by gamma of 1/4. And then, oh yeah, I forgot to list that formula over here. So give me 1 second before I continue forward. So I missed another formula. So this is another formula we'll be using in terms of gamma. And then another formula in terms of gamma we'll be using is Euler's reflection formula. So doing so apologies for missing that formula. So now everything should come together. So plugging in everything here. So 3/4 and then 1/4. And then on the new denominator, we have 3/4 plus 1/4. That's just going to equal 1. It's a well-known value that gamma of 1 is equal to 1. So we have just gamma of 3/4 times gamma of 1/4. Now, so we can actually apply using Euler's reflection formula and say that this is actually just going to equal pi of sine of pi divided by 4. And we know that sine of pi over 4 is going to equal square root of 2/2. So it's basically pi divided by this. But we can also write this and say that this is just equal to pi times the square root of 2. And so keep in mind that this value is actually just our beta value. So we just plug this back in, then we have our then we have this integral over here, the integral from 0 to infinity of 1 divided by 1 plus a squared times u to the power 4 du. Is simply just going to equal 1 divided by 2 times square root of a, and then times pi. Well, you can actually rewrite that part as pi divided by the square root of 2. So I'm going to put it that way. So square root of a, and then times pi divided by square root of 2. All right. And so that actually completes our first part of the integral that we just calculated over here. So now let's actually move on to calculate the second integral, and that is the improper integral of 1 divided by 1 plus u to the power 4. So let me actually erase this side of the board and we can continue forward. Okay, so our next integral we need to calculate is the integral from 0 to infinity of 1 divided by 1 plus u to the power 4 du. All right, and so actually this is actually applying the same thing we just actually did for calculating this integral. We do a u sub, and we actually write this in terms of a beta function. So let's take this one step at a time. So let's see, if I let u equals the square root of tangent of y, then that means du is going to equal secant square of y, then divided by 2 times the square root of tangent y dy. Then we just plug all this back into the, as our new integral. Then we have, so I'll factor out the 1/2. And then for our new bounds, of course, it's actually just going to follow from the same thing over here. So we plug 0 over here for u, then y is going to be 0. We plug infinity, then y is going to be pi over 2. So now this will be 1 divided by, so this is 1 plus, this will be tangent of, let me actually take out that parentheses. So you just plug in the square root of tangent y back into here, then we'll have just tangent square of y. Then we just multiplied, put this back in for a du substitution. So secant square of y divided by 2 times the 2 times tangent, the square root of tangent y dy. Actually, I already factor out the 1/2. So that's actually supposed to be tangent y on just the bottom. And so we have secant square y, cancel each other out, and then so far now we're just left with 1/2 times our integral, and then this is just 1 divided by the square root of tangent of y dy. And now we can actually just apply the same thing. You can say write 1 over square root of tangent y as this following integral representation. So then this will be 1/2 multiplied the integral 0 pi over 2 of cosine of 1/2 y, then times sine of negative 1/2 y dy. Then we just plug this all back in as in terms of beta. So now we have, well, you have to be careful how you rewrite this too. So this will be 1 divided by 4 of capital B. Then with these inputs, it's actually the same thing. So it's 3/4 and then 1/4. then if you just do the exact same thing, just using everything from our gamma representation and Euler's friction formula, plug all this back in, because we already just showed, technically this is just the same thing as this, we just plug this back in, we just showed that it's equal to pi over 2. Okay, and so if you just do a little bit of simplification, so that means it's just pi divided by 2 times the square root of 2. Yeah, and just like that, we've just finished evaluating this second integral. So the left-hand side over here is equal to the right-hand side. So now we can actually just, now that our integrals are solved, now we can actually just, plug this back into our f prime of a, substitution. There's still actually ways to go. I'm just gonna give you that bit of a heads up. So now plugging all this back in, so we have f prime of a, so if I just put all that substitution back in, so over here, so now we would have pi over pi divided by 2 times the square root of 2. That's actually coming from this value over here. And then I just multiplied the square root of a to the, back to the, multiply that with the 1 divided by 1 minus a squared. So this will be 1 divided by the square root of a, multiplied by 1 minus a squared. Then if you just do the subtraction, substitute that back in again for that integral we just saw, which is this. So pi divided by the square, 2 times the square root of 2, then multiplied by 1 divided by 1 minus a squared. It's also worth noting that if you go back to that, I know I erased that generalization, but if you actually plug that generalization back in for a is equal to 0, you're going to see that f of 0 is going to equal 0. So that's actually very important, because what we're going to do now is we're actually going to take the definite integral of both sides. Notice that, here, let me, I should probably reiterate this. We note that I is equal to 2 times f of 1. So we actually, if we actually take the antiderivative of this in terms of definite integral, we just plug this back in, so we get a function of f of 1 minus f of 0, which we set that f of 0 is equal to 0, which is important because we're trying to figure out what this function evaluated at that value is equal to. So coming from this, so now we have that f of 1 is going to equal the integral from 0 to 1 of f prime of a dA. And so now it's actually going to equal this following. So first I can actually factor out a pi divided by 2 divided by square root of 2. And then just from, now we have this definite integral from 0 to 1, and I'll group this. So we have 1 divided by square root of a, then times 1 minus a squared, subtract 1 divided by 1 minus a squared, and then all this with in respect to dA. Okay, and we're just about almost done. So now let's actually get rid of this side of the board and we'll continue forward. All right, so now calculating this integral over here. So let me first underline this part and then this part. Okay, so now all that's left is obviously we have to calculate this integral, but that's actually kind of difficult to see how to approach this. But no worries, because we can actually first apply a U-substitution. So let me call this new variable W, and we're gonna let this equal the square root of A. And then now just differentiate both sides. So dw is equal to 1 divided by 2 times the square root of a, then multiply by dA. And then if we'd actually just solve, because we need to substitute this in dA, so we can't do it like this. So we actually have to get everything by itself. So, well, such that dA is by itself. So I'll actually just multiply 2 times the square root of a to both sides, but we set that square root of a is equal to w. So we have a new substitution, say that 2w times dw is equal to dA. And now from here, we're actually just gonna plug all this back in. So now we have that f of 1 is equal to, so first I have a 2 over here, so if I just factor that out, then the 2 from over here will cancel. So we have a pi divided by square root of 2. Then now we just plug this all back in, so 0 to 1. So let's see, so this will be 1, then divided by, let's see, so plug this back in, so this will be w, then multiplied by 1 minus a squared, which we said that this is going to be, so this will be w to the power 4, then we subtract with 1, then it's essentially the same thing, so it's 1 minus w to the power 4, then I should also put this because the parentheses specifically because we have a w dw substitution, so not to get that confused. So w dw. Now what I can do from here is, let's say that we can actually get this into a common denominator, and so that means I'll also have to apply the butterfly method as well from here. So then we have a 1 minus w to the power 4, then subtract w times 1 minus w to the power 4, okay? And then over here, this is actually just w to the power 1 minus w to the power 4 square. Still with our w substitution, once you'll notice that these w's will cancel each other out, I can actually factor out a 1 minus w to the power 4, so pi and square root of 2. An integral, so this is 1 minus w to the power 4 multiplied by 1 minus w, and all this being divided by 1 minus w to the power 4 quantity squared dw. Then one of the quantities cancel each other out, so now we have the following. So pi divided by square root of 2, 0 to 1, and then this is 1 minus w divided by, 1 minus w to the power 4 dw. Finding its antiderivative over here, that's all it's left to do, but that's actually a bit tricky. So how do you approach this? Well, nothing more than partial fraction decomposition. However, that's actually going to be the long and tedious way, and we're actually going to skip the calculations and all that. I'll let you guys, show that as an exercise. So I want you to see that, from that verification, we get that from this partial decomposition, we will have this following. So we would have pi divided by square root of 2 divided by 0 to 1. And I'm also going to apply linearity into this for our integral as well. So we would have 0 to 1 of 1 divided by 1 plus w squared dw minus, and that's actually supposed to be a 2 on the side because that's also part of that fraction decomposition as well. Then subtract, so this is pi divided by 2 times the square root of 2, then integral 0, 1 of w divided by 1 plus w squared dw, and then the last part is add this with pi divided by 2 times the square root of 2, 1, and then multiply by 1 divided by 1 plus w dw. So essentially, in other words, let me write it this way. So I know there's a bunch of jumble of stuff that I wrote, and it might be confusing you guys. Basically, I want you to see that, or I guess I'll put this as an exercise for you guys. Show that 1 minus w divided by 1 minus w to the power 4 is equal to this following. So we have 1 minus w divided by 2 times 1 plus w squared, and then add this with 1 divided by 2 times 1 plus w. So basically this is kind of like your exercise for today, just to prove that verification works. And now, after all this, so now finding these antiderivatives is pretty self-explanatory. So obviously I'm just gonna skip those calculations because over here, this is actually its antiderivative, it's just arctangent, plug in those values. This one, you do a U-sub, and then over here, this is just actually the natural log of whatever's in the denominator. No need to do any of that U-substitution over here since it's just a basic variable of degree 1. So antiderivative is simple to find from here. So now actually calculating all those values, so we're gonna have the following. So we now have pi divided by 2 times the square root of 2. Then over here for this value is gonna be pi divided by 4. Then subtract with ln of 2 divided by 2. Add this with ln of 2. And if we just simplify all this out, then we have that this is just pi is equal to this, 2 times the square root of 2. Then pi divided by 4. Then add this with ln of 2 divided by 2. And so we see that indeed this is actually just going to equal f of 1. So we're almost done. Because the last step is, of course, we need to calculate what this is equal to. I is our given. And so we have solved what the value of f of 1 is. So essentially, simple to see that if you just plug f of 1 back into here. So now our final answer specifically is that I equals 2 times f of 1, which we see that this is 2 times all this. So pi divided by 2 times square root of 2. Well, how about this? Because this is a simple calculation, it's just 2 times the whole thing. Just notice that the 2 cancels from over here. So now the final answer specifically is that this is pi divided by the square root of 2. Then multiply by pi divided by 4. Add this with ln of 2 divided by 2. And just like that, we are done. We have solved our improper integral, another arctangent improper integral that in this series. So this was a fun one. So here you have it. That's pretty cool if you ask me.